All right, so in this video, we'll continue our discussion with partial derivatives, now talking about higher order partial derivatives. And most of what you see on the screen probably isn't going to come as much of a surprise. Let's suppose we have a part we found already, a partial f, partial x, and we want to again take the derivative of it with respect to x. So that's where your notation comes into play. Similar for y. Having already found partial f, partial y, we want to take the derivative of it with respect to y, giving us this notation. The other notation you can see would be an f sub xx and an f sub yy. Okay? Now, because there are more possible combinations here, we actually are going to have something else to consider. We've also got now possibly an f sub xy, which means that if we've already found the partial of f with respect to x, but we want to find the partial of that with respect to y, now we're going to get partial squared f over partial y partial x. Similarly over here, if we want to now go f sub yx, that means we've already found the partial of f with respect to y, but now we want partial x. Here we've got partial squared f over partial x partial y. These two things here, these are called the mixed partials. And what's interesting is many times these mixed partials can be equal. So if you look at the notation, it might seem like, well, you can just interchange these two and you'll get the same thing. And many times you're right. And if that's the case, what that means is that everything is continuous. And when I say everything is continuous, I'm talking about f sub x is continuous, f sub y, f sub xy, and f sub yx. So if these two things are in fact the same, that means all of these are continuous. And in fact, you can interchange those. That's called the theorem of Clairaut. All right, so for the first example here, we're going to look at, we're going to show and we're going to find these mixed partials and see that they are equal. So to get things started, we've got our z function up there, and I'll go ahead and start with z sub x. Now if I start with z sub x, that means my y is a constant. So as I take the derivative of this, derivative of sine is cosine. So I'm going to have cosine xy, and then times the derivative of the inside. So again, y is my constant. So the derivative of x times a constant is just going to be that constant. So maybe I'll throw that y out in front. Then I've got plus, derivative of inverse tan would be 1 over 1 plus xy squared, back times the derivative of the inside, and much like for the previous term, we would have that y that goes there on top. Okay? So then, z sub y, you can see would be pretty similar. We'll walk through it, but based upon how this was found, it's going to be pretty similar. Here, for z sub y, the x is going to be constant. So, derivative of sine was cosine, back times the derivative of the inside, where now x is the constant, so we'll have an x out in front, and then plus 1 over 1 plus xy squared, derivative of that inside again is x. All right, so there we've got our partial z with respect to x and partial z with respect to y. Now for the mixed partials, that's going to be needing to take the derivative of this guy with respect to y. So I take the derivative of this with respect to y. So now it's going to be a product rule for this first term. So derivative of the first with respect to y is going to be 1 times the second plus derivative of the second back times the first. So that's going to be a negative sine xy. Derivative of the inside, remember we're going with respect to y, so derivative of this inside is going to be the x, and then back times the first, which would be a y. So these first two terms right here, this is going to be this product rule with respect to y. And then for this term here, this is going to be a quotient rule. So we're going to have, with respect to y, we're going to have low. So we've got a 1 plus x squared y squared. Derivative of the high, derivative of y with respect to y is going to be 1. Then we've got a minus high. and then the derivative of the low. So the derivative of the low, and I've written it as x squared y squared here, so maybe that's easier to look at. With respect to y would be the 2x squared y. So the 2 gets multiplied down, the x squared is a constant, we subtract 1, so we have the 2x squared y. And then that's going to all be over the bottom squared. So that would be then this derivative, the derivative of this with respect to y. And then I'll leave it to you guys to check and confirm, in fact, that that's the same thing as z of yx. To find z of yx, you would come over to this one, take the derivative of it with respect to x. You've already found the derivative with respect to y, now it's with respect to x. And when you do that, you'll see you actually do end up with the same thing. And the theorem of Clairaut, as I mentioned, states that that's going to happen when everything is continuous. Z is continuous, these are continuous, and this is continuous as well. And when you look at the functions themselves, you will see that is in fact the case.